Welcome to Study Loop.
Problem 724, we have a 2.5 kilogram block on a horizontal floor attached to a horizontal spring that is initially compressed 0.03 meters. The spring has force constant of K. The coefficient of kinetic friction between the floor is mu K equal to 0.4. And so we're asked to find when a block and spring are released, what is the speed of block after it has moved from this position here, 0.03 meters, distance of 0.02 meters, to this point right here, 0.01 meters. At this point, the spring is still compressed. So what I'm going to do is I'm going to write down our conservation of energy formula. So we have our U elastic, that's potential energy to elastic, plus the kinetic energy in initial state, 0.1, plus work other, plus the, that should be equals the U elastic in the second position plus the kinetic energy in the second position. Okay, so first off, the easy one, it's released from rest at 0.1, so this is going to be 0. Now the other one that we can easily do is we can figure out how much work is done as the block moves from position 1 to position 2. There's friction, as indicated in the problem, between the mass and the floor below. So what we can do is we can figure out how much work is done there. So we have work equal to the integral of the force and the path length. So in this case, we have a friction force that is acting on the block. If we had put a free body diagram here, we have the block with friction force horizontal to the left, right, Fk, and that is going to be that's going to be a value that is determined by the normal force multiplied by some value mu k. And normal force in this case, since the block is not accelerating up or down, it's going to be equal and opposite to gravity. So we have the force due to friction is going to be 0.4 times normal force. So in that case, it's going to be 0.4 times the mass times gravity. So we already know the mass, we know what gravity is, so that's just a number. Then we have to make sure that we get the correct sign. So since the block is moving this way, and we have force going that way, we have a work that's going to be negative. So that's going to be negative 0.4 times 2.5 kilograms times 9.81 meters per second squared. And that's going to be multiplied by the distance. That's going to be 0.02 because it travels from this point to this point. So in all, that's going to get me a value I'll write down. So negative 0.1962 joules. Okay, so what else can we figure out in this equation? We have the potential energies of the spring. We know K and we know the distances. So we can figure out we know how to figure that out. So we have 1/2 K. I'll leave K as K, but you can plug it in for your calculations. The spring is compressed 0.03 at that point, so squared, plus this work here, so negative 0.1962 joules is equal to, we know K, we know how much is compressed there, so it's going to be 1/2 K, 0.01 squared. I'll drop the units there for now. Actually, I'll put them in there. Okay, and then that's going to be plus 1/2 mv2 squared. Okay, so we know mass, we know K. What we're solving for is V2. So I'll write down what the intermediate values are, but then I'll just leave most of the math for you. So I have 0.378 minus the 0.1962 joules. So these are joules as well, is equal to 0.042 joules plus the 1/2 2.5 kilograms V2 squared. Okay, and then so that should just get us a final velocity equal to 0.33 meters per second at that position 2, where the spring is still compressed. And that should be to the right.